Good morning. Today, I'd like to begin talking about vector calculus in special relativity. In particular, I'd like to talk about four vectors: the four velocity, the four momentum, and the four force. To begin with, we're going to do things in a way that is very similar to how we did it in third semester calculus or the analogous calculations in linear algebra. To begin with, let's suppose that we have 2 points of space-time, P and Q. I have not introduced any coordinates or inertial reference frames. I just have space-time and 2 points. Presuming that the geometry is Euclidean, I can draw the straight line segment from P to Q and think of it as the vector from P to Q. A vector for us right now is an arrow. I'll probably say a vector is an arrow many times before we're done. If I introduce a coordinate system, an inertial reference frame, I can identify P with quadruples of numbers T1, X1, Y1, and Z1. Likewise for Q, just as we did back in third semester calculus, the vector that goes from P to Q is going to be a quantity, which is an arrow. It's going to have a certain length to it and a certain direction to it. Again, as in calculus 3, we figure the components of the vector as being the difference of the ending coordinates minus the starting coordinates. If this were actually calculus 3, we would write things like the vector from P to Q equals, and then bracket, difference of coordinates, difference, difference, and the difference of the z's. But one of the things we're very interested in special relativity at least, is changing from one coordinate system to another, and there is no guarantee that when we change coordinate systems, these components are going to be the same numbers as they were in the system that we started with. So rather than adopt the notation that we did back in third semester calculus, we're going to say that the vector from P to Q, this arrow, has components with respect to O of the differences of coordinates as measured by O. If I were working in a different inertial frame, say O bar, I would say instead T bar 2 minus T bar 1, and likewise for the other components, those numbers could be completely different from T2 minus T1, and so on. I should never, under any circumstances, write that. At the moment, it wouldn't cause us huge amounts of trouble, but when we jump to non-flat coordinate systems and non-flat spaces, it will. As we begin to shift to our actual notation that we're going to use, we'll introduce the following ideas. Instead of writing t, I'll write x0 with the 0 as a superscript. Instead of x, I'll write x1 instead of y, x2, and instead of z, x3. Our coordinates are always going to be represented by a letter with an index. We will define the addition of vectors with respect to some frame in exactly the same way that we did in Calculus 3, except we have 4 components now instead of just 3, indexed 0, 1, 2, and 3. Likewise, we define subtraction as you think we would, and we'll define multiplication of a 4 vector u by a number alpha in the same way that you did in Calculus 3. It was around to this point in third semester calculus that you introduced the idea of the ijk basis vectors. This is an arrow. This also is an arrow given in terms of numbers that are measured with respect to some inertial frame. This is an arrow. The numbers u0, u1, u2, and u3 are a description of that arrow using the unbarred coordinate system. Because of the way we add vectors together, I could write it as this one plus that one plus that one plus the last one. Each one of these things are arrows. So should I write arrow with an O above, or should I write an equal sign? Very soon the distinction will be important. We do vector addition if we want in terms of the components, but even if I hadn't set up a coordinate system, I can still make sense out of what the arrow a plus b is by using our parallelogram. So you should think real hard about this. This as compared to this. Arrow with an O above it or equal sign. Vectors are going to represent physics to us, so I can't emphasize this enough. If I give you 2 arrows in space-time, because we assume geometry is Euclidean, I can move the initial point of the 2 vectors to the same point, form the usual parallelogram, and tell you what the arrow u plus v is, or the arrow u minus v, or if I tell you what u is, I can draw u, draw a copy of u, and call that 2u, draw the arrow u, then draw it again, except interchange the initial and terminal points so as to get negative u. Everything that we know about up to this point works just as it did back in third semester calculus. If we set up an inertial frame, O, and we have an arrow of space-time, we can measure the difference between the ending O coordinates and the beginning O coordinates of the vector u. I'll call the resulting numbers u0, u1, u2, and u3. The reason that I don't say equals instead of this funny symbol is if I used some other inertial frame, the u arrow would be the same arrow in space-time, but the numbers could very well be different. In terms of the components, we're going to make an analogy and do things exactly the way that we did them back in Calc 3. When we write this, we mean that if I take the arrow in space-time, never mind what coordinate system you're using, and another arrow, I'm going to form a new arrow whose name is u plus v. The components of this u plus v could be measured in any inertial frame, but we're going to define things so that when I use the same inertial frame that the components of u and v are expressed in, we simply add corresponding components, just like we did in Calc 3. We do something similar for subtraction. In the issue of multiplying a number by a vector, we have to be a little bit careful here. A vector is an arrow. It's an arrow of space-time. It is what it is. It may have different components depending on which coordinate system you're using. If I want to multiply such a thing by a number and have the result come out to be an arrow of space-time, with the arrow being whatever it is, independent of the coordinate system, we have to be careful. The number that I'm going to multiply a vector by, in order for this to make sense, is a scalar. Now, in ordinary calculus 3, when you say scalar, you just mean a number, not a vector. We mean something more than that now. A scalar is a quantity that is a number, and for a given situation, that number does not depend on which coordinate system you're using. So the alpha, a scalar, is a number which is frame independent. Given that little bit of refinement to our thoughts, though, number times vector is the same thing that you did back in Calc 3, except now we have 4 dimensions to work with instead of just the 3 as before. U is an arrow. This is an arrow, so is that, and so is that. What about these numbers u0, u1, u2, and u3? When we change to a new coordinate system, the components of the vectors will change, but if you think very carefully about it, u0 is the initial component of vector u as measured by O. No one else can tell O that he didn't measure what he measured. So even if you ask some other inertial observer, O bar, what this number is, if he's speaking carefully, he'll say it's the initial component of vector u as measured by O. If you had another inertial frame, O double bar, and so on, they would say the same thing. If you hold your head just the right way, these numbers, u0, u1, u2, and u3, are scalars in the sense that we just mentioned, because no one can tell O what O measured because they're in a state of relative motion. That would literally violate the principle of relativity. So when I write this as compared to this, I don't have to write arrow with an O above it. I write an equals. Because of the way we multiply a scalar by a vector, I can write this sum this way. We're going to give special names to those 4 vectors whose components with respect to O are known to us. We're going to call the vector whose components with respect to O are 1, 0, 0, 0, we'll call that E0. This one we'll call E1, that one we'll call E2, and that one we'll call E3. E1, E2, and E3 would be I, J, and K if we were back in Calculus 3. Each one of these vectors is a vector that starts at the origin of O and has its endpoint 1 unit bigger in a given coordinate direction than the origin does. In this one, you allow the time variable to increase by 1 unit, but you hold everything else the same. Here, you start at the origin, let the x-coordinate increase by 1, but keep everything else the same, and likewise for the last two vectors. Having indexed things in this way, I can write vector u as the sum of the components of vector u with respect to O multiplied by the corresponding basis vector as measured in O. There are several issues, notational and otherwise, about this. The first thing is, as we do our work, very often we're going to have sums of this general type in which the index of summation appears above in one place and below in another. In some of these calculations, if you were to actually write it all out, even with the sigma notation, life would become very complicated. So here is the first of several refinements that we'll look at. The Einstein summation convention says this: in a product, if you see an index that appears in an upper position, and then somewhere else in the product that index appears in a lower position, unless we say specifically otherwise, we assume that to be an index of summation, and we don't actually write the sigma down. So using the Einstein summation convention, vector u is equal to u mu e mu. When something is an arrow, we write an arrow above it. When something's not, we don't. As long as I don't get into any naming conflicts, I can change the name of an index of summation to be anything I feel like. So u mu e mu is the same as u alpha e alpha, which is the same as u gamma e gamma. When we do a Lorentz transformation from O to O bar, the relationship between the barred coordinates and the unbarred coordinates are linear. That is to say, like this, where A, B, C through P are numbers that don't depend on x0, x1, x2, or x3. We are going to adopt a notation for this. Since I'm calculating x0 bar here, all the coefficients in this first equation are going to have an upper index 0 bar. All the numbers that are coefficients in the second equation will have an x1 bar, likewise x2 bar, and x3 bar. In order to write this in a very compact form, within each one of these equations, when I multiply by x0, the lower index on the coefficient will be 0, x1, 1 for the coefficient, x2, 2 for the coefficient, and x3, 3 will be the lower coefficient index on the lambda. If I take advantage of the summation convention, I can write these four formulas in a very compact way. Of course, a clever person will notice that the only difference between these four formulas is that I have a 0 bar upstairs in both of these, 1 bar in both of those, 2 bar, and 3 bar. So if we wanted, we could write the whole thing as x mu bar equals lambda mu bar nu x nu, with the understanding that the nu is an index of summation, and since the mu bar does not show up upstairs and downstairs in a product, it is not an index of summation. This formula is supposed to be true for all possible indexes mu bar, which could be 0 bar, 1 bar, 2 bar, or 3 bar. This is going to be our new way of writing that. So we have compressed all of this stuff down into one line. It's absolutely vital that we not goof up what we mean. This is actually 4 equations. Each equation has 4 terms in it. There are things being multiplied together and added up. Suppose you have 2 points of space-time, P and Q. I use the coordinates of O to measure P and Q. For P, I get x0, x1, x2, and x3. And for Q, I get y0, y1, y2, and y3. And minus star tells me that as measured using the coordinates of O, the components of vector u, being P to Q, is and minus star. What are the components of vector u as measured using the coordinates of O bar? I would have to figure out the coordinates of point Q according to O bar. I'll call those coordinates y mu bar, and I would have to subtract away the coordinates of point P as measured by O bar. I'll call those coordinates x mu bar. There are some comments to be made about this notation, but I'll put that away for a minute. We've just decided on a new notation for our linear transformations. Y mu bar is lambda mu bar nu y nu minus lambda mu bar nu x nu. In both of those terms, there's a sum, the sum over nu. I could think of writing that out, combining the two sums into one, and then expressing it using the summation convention again. Component number mu bar of vector u is lambda mu bar nu, don't forget the summation convention, y nu minus x nu, but y nu minus x nu are the components of vector u as measured by the O coordinate system. That is to say, u mu bar equals lambda mu bar nu u nu. The components of a vector as we have defined it obeys the same transformation rules that the coordinates themselves do. This is going to let us figure out a whole bunch of stuff. Before we reverse these transformations, I want to make a comment. In the formula for one of these barred components, you have coefficients, constants, with respect to the components of u. That means that lambda mu bar nu is just the partial derivative of x number mu bar with respect to x number nu. At the moment, that statement doesn't mean a whole lot to us, but when we jump to non-flat situations, this will be our wedge into curved spacetimes. Along the way, I've tried to emphasize the fact that it makes absolutely no difference which one of these inertial frames we call O and which one we call O bar. This is still true. Every comment that we've made so far can be made in the reverse sense. If I started off knowing the components of an arrow in the barred system, exactly the same logic would lead me to the conclusion that U alpha, component alpha of U as measured by the unbarred system, is lambda alpha gamma bar times U gamma bar, where lambda alpha gamma bar is the partial derivative of x alpha with respect to x gamma bar. We will take this as an accepted fact. I want to make an observation. If you had an ordinary matrix in linear algebra and you interchanged the row and column index, then you would just be rearranging the numbers in the matrix, but they would be the same number, just in different locations. There is absolutely no reason to believe that any of those numbers and any of those numbers are the same. In fact, they're usually not. One way to think about these lambda numbers are, since they have two indexes, they're kind of sort of matrices. I'll think of the upper index as being what row I'm in, and the lower index as being what column I'm in. These numbers, generally speaking, are not the same as those numbers, not even in the sense that they have been rearranged in a matrix. I want to look at the relationship between these two things. I want to look at lambda mu bar nu lambda alpha mu bar. So I'm going to be taking numbers out of one of these sort of matrices, multiplying by others, and then because the mu bar is the same, I'll be adding up stuff because of the Einstein summation convention. If you look at that, that should seem very familiar to you. Back in third semester calculus, when you looked at the chain rule for multivariable functions, you got something that looked very much like this. Applying the chain rule, this big messy looking expression just turns out to be the partial derivative of x number alpha with respect to x number nu. Notice there's no bars or anything in that. I'm in a certain situation where I'm using the unbarred coordinates. The coordinates are independent variables. The partial derivative of one of the coordinates with respect to a different coordinate is 0. The partial derivative of something with respect to itself, of course, is 1. We will create a special symbol with two indexes to be put in the appropriate places for this situation. We will call it the Kronecker delta. Delta with alpha upstairs and nu downstairs is a number. That number is 1 if alpha and nu are the same number, and 0 otherwise. If you think of the alpha as being the row index and nu being the column index, this would be a matrix that's 0 every place. Except that it's 1 on the main diagonal. This is a fancied up way of writing the identity matrix. I'm going to rewrite this in ordinary matrix language. So lambda mu bar nu, I'll think of being a matrix element out of row mu bar, column nu. Lambda alpha mu bar, I'll think of being an element of some matrix in row alpha and column mu bar. In this equation, mu bar is an index of summation. I'll think of delta alpha nu as being the element out of a matrix with row index alpha and column index nu. If I become literal-minded and put the sum back in, then I'm going across row alpha of L and down column nu of M, multiplying corresponding things and adding them up. But that's the definition of how you multiply matrix L by matrix M. Component number alpha nu of Lm and component number alpha nu of I are the same number. The numbers that are in matrix Lm and the numbers that are in the identity matrix in corresponding positions are equal to each other. That is to say, L times M is the identity matrix. L and M are inverse matrices of each other. These numbers are the numbers out of a certain matrix. Those numbers are the numbers that come out of the inverse of this matrix. So we have to be very careful about the placement of the bar and no bar index here. But of course, one inertial frame, one flat coordinate axis coordinate system or another, is as good as any other. If you go through the exact same argument, you can show that lambda mu bar beta, lambda beta nu bar, is equal to delta mu bar nu bar. The last thing that I want to do today, because this video is starting to get a little on the long side, is we now know how the components of a vector change when you go from one frame to another. I'd like to do the same for the basis vectors. Imagine that I have a vector v, an arrow of space-time. I could write its components using the unbarred coordinates and use the basis vectors from the unbarred coordinates and write v equals v alpha e alpha, where of course the alpha is an index of summation. Or I could use the coordinates of the barred system and the basis vectors that go with the barred system. The arrow v is also equal to v beta bar e beta bar. These are two different formulas that tell me the same arrow. Two things that are equal to the arrow v must be equal to each other, so this must be true. On the other hand, we have just now found out how to express v beta bar in terms of the unbarred components of vector v. V beta bar is lambda beta bar mu v mu, so this must be true. On the left side of that equation, there's a sum. The index of summation is alpha, an unbarred index. I can replace the letter alpha with any unbarred letter I feel like, and it doesn't make any difference since it's just an index of summation. Really, I should say any letter except V and E, because that would get confusing. So what I'm going to do is I'm going to index things so that certain things match up. I'm going to replace index alpha with index mu. The reason that I'm doing that is this will make the upstairs index on the V mu, which will match that one. Then subtract the quantity on the right from both sides, and you find out that a certain thing must be 0. Now, this is a sum over index mu. There is also a sum over index mu in the second term. If you don't believe it, write out all the terms, but this turns out to be true. Where I am still doing a summation over index mu. Now we have to be careful. I'm going to get a result in a minute that looks like I just divided through by the V mu, but that makes no sense. Thinking only about what goes on with mu, there are 4 different things being added together here. One of them has V0, another V1, another V2, and another V3. So there can't be any idea of just dividing that V mu out. That doesn't make any sense. On the other hand, I didn't say anything about which vector V was. This needs to be true regardless of which particular vector that you pick. So we're going to pick some interesting particular vectors. If I pick V to be E0, the time basis vector of the unbarred system, in unbarred coordinates, that has a component 1 at the front and then 3 zeros. When I form this sum, only the mu equals 0 term is going to survive, the others being multiplied by zeros, and we find out that the following is true. On the other hand, I could pick V to be the first space coordinate vector. In this sum, when mu is 0, the V component is 0. When mu is 2 or 3, the corresponding component of V in the unbarred system is 0. Only the V with a superscript 1 term survives, so the following must be true. Not to be too obvious about it, but you'll get corresponding facts if V is E2 or E3, the Y and Z basis vectors of the unbarred system. It turns out that these kind of facts are true for index 0 downstairs, 1 downstairs, 2, and 3. In general, for every index, mu equals 0, 1, 2, or 3, this quantity must be 0. And see, this looks like the world that I've just divided the V mu out, but that's not what's going on here. In any case, when the dust finally settles, this tells me how to express the unbarred basis vectors in terms of the barred ones using these coefficients that we know stuff about. So we've figured out how to do the barred components of a vector in terms terms of the unbarred components, the unbarred components in terms of the barred components, how to express unbarred basis vectors in terms of barred basis vectors. In addition, we've identified what these coefficients actually are and found two properties that will be very useful to us. The only thing I haven't written down on my list here is how to express the barred components in terms of the unbarred components. I see two different ways of doing that. One of them is to invoke the principle of relativity and say it's obvious how to do that. And the second one is to do some minor linear algebra manipulations. I'll work with this formula. Let's think about the indexes. Beta bar isn't really there. It's an index of summation. So if I were going to move something around, there's no point in trying to move the beta bar. I'm going to do something with the mu, though. I'm going to multiply both sides of the equation by lambda mu gamma bar, where now mu will be an index of summation. Over on the right, I'm adding up over index mu. I'm also adding up over index beta bar. I can add those terms in any order that I want to. So I'll think of adding over the mu first and then see what happens. Lambda mu gamma bar lambda beta bar mu is the Kronecker delta based on beta bar and gamma bar. On the other hand, beta bar is still an index of summation, so I'm going to take various numbers, multiply them by various basis vectors from the barred system, and add them up. But these delta numbers, delta beta bar gamma bar, they're all zero, except when beta is equal to gamma, in which case you get a 1. So the conclusion is that E gamma bar is lambda mu gamma bar E mu. Einstein and others set this notation up so that things would be easy to remember. We write the components of a vector upstairs because that's how we were writing the coordinates. We figured out that upstairs mu bar, alpha alpha index of summation. Beta upstairs, nu bar, index of summation. Mu downstairs, beta bar, index of summation. Gamma bar downstairs, gamma bar, and mu is an index of summation. These formulas almost write themselves down if we can remember this pattern. So we've talked about vectors as arrows. The parallelogram law still works for addition and subtraction. We know about component form, addition, subtraction, and multiplication of a vector by a scalar quantity. We know about basis vectors. We've mentioned the summation convention, and taking all of this stuff into account, all of the things we know about vector components and basis vectors to this stage are these facts, and these facts. I'm going to stop here for today. This is beginning to get a little out of control. We'll talk more about this as it relates to physics next time. Until then, I hope everybody has a good day, and I'll talk to you again soon.